So I'm going to talk about Lucene today. That's what I was asked to talk about. But if people want to hear about anything else that I've worked on, or anything else that's bugging them, I'm happy to talk about that instead. So if people are looking bored, I can rush and we can have more time for Q&A at the end. We can do it how you want. So it's kind of 2 talks in one. We're going to do the Lucene Classic and then the new Lucene talk. And so I'm going to start off first with a sort of timeline of giving an overview of what's happened with Lucene through the years. So Lucene was born in late 1997. I was working for Excite, a web search engine. How many people here ever used Excite? All right, a couple, quite a few. Java had just sort of come out, and I thought Java looked like a cool programming language, and I was worried that the internet bubble was about to pop. I was 3 years early in my prediction. I was concerned that my career wasn't very solid working for a web company. And so I wanted to have something to fall back on. So I actually went down to 60% time at work, took 40% time, 2 days a week, stayed home, and taught myself Java, and wrote Lucene. The name is my wife's middle name. I think I did that in about 3 months. And then the web thing started to pick up again for a while in the late 90s. Then when Excite went bankrupt in 2000, I decided to make Lucene open source because I didn't have anything else to do with it. I realized I didn't really want to start a company. I wasn't an entrepreneur at heart. Now, when I originally started it, my goal was to aim for sort of a niche of folks who wanted a search engine for a moderate number of documents, like maybe an encyclopedia or all of your email or the files on your hard drive, not for great big things that would be running on servers. And I thought that Java was possibly going to be a language that would be used for lots of sort of embedded software. So I was aiming for maybe 1 million documents, maybe 10 million documents at a stretch was sort of the design goal for Lucene. This was in the days before Java really had a JIT. I think I first wrote against Java 1.1 and 1.2, as I recall, was the first one that had a JIT compiler. So it was performed a little differently. Hardware was also a little slower in 97, 98. Since then, we've seen Lucene has grown quite a bit. I initially posted it to SourceForge under the GPL because that's what I thought open source meant. The only license I knew anything about was the GPL. And people started complaining. They said, we can't use this thing. And that was frustrating to me, that I was trying to give something away that people could use, and I wanted people to use the software, and they said, we can't use it because of the license. I changed to LGPL, and a few people said, well, that works, but other people were like, no, we still can't use that. Around that time, folks from new thing in town called Apache said, hey, you should come join us, we're really cool. I was like, okay. So we moved Lucene to Apache, used the Apache license, never heard a complaint again about the license, about people's ability to use it. So that's my sort of capsule review of open source licensing. If your goal is to get people to use the software, then a BSD style license works a lot better. And that's always been my goal, is to get adoption, and then you get contributors and so on. Lucene, gradually got more and more folks using it. 2004 became a top-level project at Apache. 2006, Yannick Seeley and some other folks at CNET, I believe it was, came out with this sort of server version of Lucene, or wrapper around Lucene called SOLR. And then 6 years later, we saw finally a scalable distributed version of SOLR, of Lucene, in wide distribution. And the version I'm going to talk about mostly, there's a couple of people who've worked on that style of system. But the one I'm going to talk about is SOLR Cloud primarily. And then a couple years ago, we started to try to integrate Hadoop search into the Hadoop ecosystem. And I'm going to spend a lot of time on that, talking about why I think that's interesting. All right, so now I'm going to take you way back. These are some slides that I wrote initially, I think around 98, maybe 99, before it was even an open source project. And they still more or less describe what Lucene is. So there's this sort of fundamental block architecture to Lucene. The heart of it is the indexing, where you store some representation of statistics about documents that you can use to accelerate searches. So you've got at the top level an application API, which lets you add documents to the index and make searches. There's this thing Lucene calls analysis, which has to do with taking text and getting terms and tokens out of it, figuring out what are the things in that text you want to index and you want to search over as well. So analysis is used by both search and it's what is fed into the index. And then underlying it all, this general abstraction of storage, of where are we going to store these indexes? Probably files on hard drives, but maybe in memory, maybe other places. And I think this is was a wise design decision to have an abstraction underneath. I think it's provided a lot of utility to Lucene over the years, some of which we'll talk about as we go. So what differentiates Lucene? One of the things was the way that indexing is done. If you looked at textbooks and most people who were doing search at that point, they talked about big batch processing, giant sorts of data files for fairly static collections. And that works pretty well. It gets a little tricky when things are distributed, but in general it works pretty well if your collections are static. But a lot of times you want to be able to search things that are changing. So I wanted to do an indexing data structure that was somewhere between a static sort and something that was indexing things on the fly. Other approaches that I saw around those days were some people would just make an index for every 16K documents, and then you'd search them all. And that scaled pretty poorly when things got big, because you had a lot of little indexes to search. Other approaches were to use something like a relational database, or the data structures that are used by a relational database. Use a B tree. Use some sort of dynamic data structure that's paged off disk. And this works horribly. I tried this as well. They get really fragmented, and you're doing crazy amounts of seeks and totally I/O bound. So what I came up with sort of a hybrid technique, which is, I believe, more or less the way Lucene still represents indexes, which is, I'll try to walk through this. Again, this is an old slide. Probably there's better ways of drawing this, but I brought it out for historic interest. If you think of documents being added over time from left to right, and you've got 3 documents added, and as each one's added, you build an index for it, an index for one document. Then when you've got 3 indexes, so here our magic factor, we call the merge factor, is 3. When you get 3, you merge it together and you create a single index for 3 documents. Continue on, it should be getting obvious now. 3 more, you make another one. 3 more, you make another one. Then all of a sudden you've got 3 of size 3. You can merge those together and make one of 9. So what this really is merge sort. But it's merge sort where you're merging incrementally as you go, as things are added. You don't know the total size of the thing you're going to merge. And instead of having the future merges on the runtime stack, on the call stack, as you would in a recursively coded merge sort algorithm, you've actually got an explicit stack that you're storing on disk, which represents the state of the merge sort. Hopefully that makes sense. Seeing a lot of sort of blank faces out there. Maybe you're just bored. All right. So that was some novelty. So this has a lot of nice properties. You can incrementally add documents. You make these tiny documents. The bulk of the index ends up in these larger ones. You can do these merges in the background. In general, it's optimal. You're doing a merge sort. So you're doing n log n compares of terms and IOs and all these parameters which you care about. One thing I don't mention here is all the IO is sequential. That's a nice property of merge sort over reasonably large batches. So it behaves well on hard drives. Moreover, you can search it when you're as you're indexing. But there's no final index state. As you're going along, you've minimized the number of indexes you have to search, or at least bounded to some reasonably low bound. So it gives you this nice compromise between doing some giant batch process periodically or having searches that are really slow. It gives you searches that are reasonably fast as a collection changes. And it's worked pretty well through the years. Still, as I mentioned, the predominant way that Lucene indexes are built. On top of this, we added a number of search algorithms. It's extensible. People have continued to add new kinds of search on top. The fundamental two types are ranked search, where you're sorting by some measure of similarity between the query and the documents. This is sort of what we're used to on Google. Or you can sort them by other criteria, as you're used to on various shopping engines. You might want to sort by price. You might want to sort by date, by whatever. And so both of those are supported in Lucene, both of those styles of search. Another interesting difference from a lot of textbook search algorithms. At the time, there weren't a lot of other open source search engines to look at. So all I had to go by was sort of what was in the literature. And most of them, the amount of memory that was consumed while searching was proportional to the collection size, which seemed problematic to me, especially if you wanted to be running multiple queries simultaneously. That can add up to a lot of memory. So the way that Lucene's queries work is that the index is, in effect, streamed through. The relevant parts of the index are streamed through the query processor. And so that the memory that you require while you're searching is mostly proportional to the query, not the collection. And that's, I think, still the case. There's some exceptions. There's some things that get cached, but they tend to be things that are reused by lots of queries rather than per query data structures. So we started out with, from the beginning, supporting Boolean searches, phrase searches. Since then, various other kinds have been added. Range searches, spatial searching, span searching. Who in here has ever used a span query in Lucene? I got one hand back there? All right. You rock on. I'll buy you a beer later. Those are, I've always had a soft spot for span searches, but nobody ever uses them. Anyway, there's other features. We can skip through this. So as this engine got adopted, a community grew around it. This is sort of where I learned about community open source. As in the early 2000s, we started getting, first thing we saw, analyzers for other languages, stemmers for a variety of languages added. Highlighter, so you can see the terms that match the query can be highlighted in fragments of search results. Not a totally easy thing to do well and in a reusable manner. Completions, so that if you're typing a query, you can see some candidate completions. These days, these are a source of humor, Google completions. Spell checking. If people are typing something that there isn't a lot of in the index, but there's a lot of things that are similar to that, you might suggest some other terms. So we started to get these kinds of contributions. We got SOLR, obviously, a huge contribution, providing a set of web services that give you access to the functionality of Lucene. and APIs to access these from a variety of different languages really brought Lucene to an audience outside of Java programmers. And I guess everybody here is a Java programmer, so maybe you don't care. But there are other programming languages out there, and they were happy to be able to, the programmers of those languages were happy to be able to use Lucene. Another thing that SOLR really focused on were facets. Facets, for who's familiar with the term facets in search, these are these things, yeah, a lot of people are. These are the things you see like on the side when you're searching in Amazon or Netflix or a lot of search engines that give you ranges of prices, maybe manufacturers, sizes, these kinds of things. And they're actually generated automatically based on the result set that you're seeing. So depending on what your query is, what facets are the best ways to distinguish those result sets vary. And it can determine those dynamically. So SOLR really brought faceting to the Lucene world. And it's been improved a lot through the years since then. And moreover, it just got adopted by a lot of folks. And I should have moved Twitter to first position here, but Twitter is Twitter search is powered by Lucene. Wikipedia is powered by Lucene. LinkedIn, Netflix, I think the iTunes Store, as I understand it, is Lucene based. Salesforce, it's kind of the search technology that has ended up behind most search engines except Facebook, Bing, Google. The very biggest of search engines tend to build custom things. Not that Twitter isn't big, but Twitter is good at reusing technology that's out there rather than reinventing things. So anyway, it's seen a lot of adoption. A couple of books written about it. Companies built around it, businesses built. So it's really become an established component of the software ecosystem. Really taught me about the possibilities of open source. I don't think that Lucene would have done this, would have achieved these things, had it not been open source. Had I tried to build a company around this from the outset, nobody would have heard of it. The company would have gone out of business. I believe there were other companies much larger, much more established, selling search technologies. Maybe their search technologies were worse, maybe they were better, but I think people picked up and started using Lucene because they felt comfortable trying out something that was open source. They found the project approachable. It's kind of another talk. If you have more questions about open source, be happy to talk about that. But I think it was really the key to getting this and got me very excited about the possibilities of that methodology. So now I'm going to zoom forward to nearly the present day. In the last couple of years, Cloudera decided to try to figure out what it would mean to add search into the Hadoop ecosystem. As most of you probably know, Hadoop started out as a very scalable batch programming system, generally used in sort of back-end processing. Had various things added to it, HBase, sort of online key value stores, SQL engines of various sorts. And it seemed to us that search would be a useful component to have there too. People get search. It's a nice complement to all these other tools. And it brings a much wider audience to your data if you can make it searchable. So what should we do if we're adding search to Hadoop? How should this look? It seemed to me the critical thing was that it needed to be really well integrated. It needed to be a first-class citizen. And we already have search as a standalone thing. And the real advantage of the Hadoop ecosystem is that things aren't standalone, that they're integrated with one another, that you have one copy of data that multiple applications can share, that you have one security framework, one management framework, You can bring all these things together, one pool of hardware that you're sharing, and achieve some real economies of scale and of usability by doing so. So that was the key. So the trick was figuring out how to make this work. People had tried putting Lucene indexes in Hadoop, in HDFS, in Hadoop's file system for years. I had started trying that probably before it was called Hadoop, back in 2004 timeframe when we first, when it was still NDFS. And it was horribly slow to put a Lucene index in the distributed file system. And most people, myself included, you tried it, said, it's slow, and sort of walked away and said, oh well, we'll just keep keeping indexes on the local drive. Aaron McCurry, a guy who lives in DC, actually figured out why it was slow and figured out how to make it more quick, make it faster. Actually, I'm going to come to that in a second. No, I'll skip to it. So he figured out what the problem was, and the problem was a really simple one. HDFS doesn't have a client-side cache of I/O. It doesn't have any cache, really, of I/O. There's some on the server side in the server's buffer pools, but you may or may not be using that very effectively. And Lucene really depends on having a client-side cache of file I/O. And that one trick of adding a client-side cache got performance of Lucene running out of a distributed file system to be pretty much comparable to running off a local hard drive. It really wasn't that hard. So Aaron added that in the Blur project. That's since been backported up into the Lucene project, and I believe is in the most recent releases of Lucene. You can now search indexes in HDFS quite efficiently. So stepping back a second, the thing we ended up building, the choices we made, were to put SOLR integrated into CDH, and to do so as much as possible using existing projects. So I'm not describing a new open source project here. What I'm describing is a set of integrations that are made to a number of projects, which I'm going to go through. And as much as possible, we're trying to put these integrations upstream into the respective projects. I think there's one exception of something that is actually a new piece of software. But for the most part, it's just a series of integrations which, when you view them as a whole, give you this thing where you've got search all of a sudden as a part of the Hadoop ecosystem. So it's all open source, just about everything I'm going to talk about. So I'm going to go through and talk about these various integrations. First one is one that just comes from using SOLR. SOLR supports a lot of different document formats. And so it has this system called Tika that it uses, Apache Tika, which helps doing document conversion from PDFs, HTML, and so on. And so that gives us a big advantage right there. We can just pick that up and use it. But integrating with these other components of Hadoop took some work. So first, we worked on building a system that let you build SOLR indexes using MapReduce. And this is a huge advantage because it lets you, if you have to build your index as a batch process, say on a nightly basis, which for a lot of, depends on what kind of data you're indexing, but there's a lot of types of data where this is a reasonable way to go. You really can't do things, do everything incrementally. This is a great way to go because you get all the advantages of MapReduce, all the efficiencies, and you end up with the indexes right there in HDFS on your cluster, ready to serve. So it's a very efficient way to, as a batch, build SOLR indexes. It's more efficient than running a SOLR cluster and trying to throw all the documents at it and index them in the normal way. As a variant of this, you can run a MapReduce job and build a bunch of and write a bunch of updates, build a bunch of new indexes, and then switch to them atomically and make this new system live. So if you have a running search system and you want to do a big bulk update to it, you can use MapReduce to do the bulk update and then switch to it and flip over to the new index. So this is sort of a combination of having a running system that's operating incrementally and then combining that with some batch operations. So we've added some hooks to support that as well. Then we've also worked with integrating SOLR with Flume. So if you've got, say, events streaming in from logs, your tailing log files, then you can have every event as it's generated go into an index so that they're searchable within seconds of the time they occurred. So if you can have what we call near real-time search of events from log files or from whatever sort of streaming data you might have from a Twitter fire hose, for example. So here we see that you can also tee the logs into HDFS, but you can just, as they're coming in real time, be indexing. Another integration is HBase. So this hooks into some hooks that HBase has to support replication, so that you can be notified every time anything changes in HBase. So you don't actually get in the way of the actual operations. It runs as a parallel sort of process. So as changes are made to HDFS, the changes are streamed into an index and again updated in near real time. So another nice integration. The one new thing that we ended up adding is a system called Morphlines. So if you're building Lucene indexes, you tend to have some source of data that you want to index, and it comes in whatever native format it is, and you have to decide, okay, I want this. Let's say you've got a log of a web server, and you want to it has IP addresses, it has queries, it has query strings, and you want to index these different components of the log in different ways for each event. You may want to index the IP address as a number. You may want to actually look up the latlon, the location of the IP, and index that. You may want to index individual keywords from other parts of the URL so they're separately searchable. You might want to index the whole URL so you can do prefix searches on it. There's various things you might want to do. So there's a little bit of logic that it takes for each search application to take the incoming objects and get them into the index. And for anybody who's written these kinds of programs using Lucene, they kind of all look the same. You have some Java code, which is piecing things together and reading the input and adding to the index and da-da-da. So Morphlines makes this, instead of having to maintain a Java program, which is, and build it and build a jar file and push it out to wherever you're running all this. Instead, you can do this all in a config file. So you can specify processing pipelines, including bits of Java code, including bits of logic, that get incoming events, process them, and then emit Lucene documents. So it's a ETL engine, if you will, that's can be used here, can be used in lots of other places. It's a general purpose tool. It's just a Java library that you can use and compose these pipelines specified as config files. So then all you have to do is update the config file, and everybody will see it and start processing things in the new way. So it's an easier thing to distribute because we're sort of used to distributing configurations, and it actually opens these kinds of operations to a much wider pool of folks. If you want to change the way a field is indexed or add a new field into indexing, you don't necessarily need a Java programmer. It can be a very simple operation of applying a regular expression to the log line, extracting something, and specifying it as a field. You'd like to make that simple, those kinds of things, and make it not something that requires programming. And Morphlines lets you do this. So I encourage you to look at it. It's got good documentation. Here's a quick sort of example where you might have a three-component pipeline. You've got Flume tailing a syslog, which is then coming into the SOLR sync, which will run the Morphline. So you're preparing the stuff you're going to index. You're going to read a line at a time from the log. You're going to apply some regular expression to it, and you're going to create a document which you're going to load into SOLR. So it's fairly straightforward. Right. Another thing that we did was we added into Hue. Hue is the web interface for Hadoop that I think just about all of the vendors are using these days. We added a search interface that talks to SOLR into that. Now, you probably can't see this very well. This is a Twitter search engine built using it. And if you look at it, it's a decent web UI for Twitter search. You've got tweets, you've got the avatars, you've got the poster's name, you've got a link to the tweet itself, you've got the hits highlighted, you've got some facets automatically generated on the side. The neat thing about this demo is there was no code involved in it. This is just taking an index that grabbed the fire hose and took a little Morphlines. I think all this code is out there. You can find this demo on the web. And index the Twitter stream. And then you come up with this very generic interface in Hue, which has no configuration, will work for absolutely any Lucene index in the world. And then you can customize it all through the web UI. You can tweak it and add little bits of HTML, little bits of style sheet here and there, and end up with this. And there's a great YouTube video demo of doing this, where they actually build this demo from the ground up in about a 3-minute video. So it's a pretty nice tool if what you're trying to build is a quick UI that you can give to folks, and you don't want to spend a lot of time, a lot of developer time building a search interface. A nice bit of integration again. So sort of in summary of what we've done here to get Lucene into Hadoop, into the Hadoop world. We've had an integration with Flume, so you can index things that are streaming in. We've got an integration with HBase, integration with MapReduce. So all of these components can modify and create indexes. And then you can search it in a variety of ways. You can search it using the Hue interface I just described. You can build a custom web interface using SOLR's well-known web interface, web API. Or you could build a custom interface using the various API bindings for SOLR that are already out there. So it's trying again to reuse as much as we can of the ecosystem and just to make search a first-class citizen of this platform. Lastly, if you're the sort of person who wants to use cluster management tools, this is not open source, this is Cloudera's manager. You can use this to deploy and configure and monitor your search cluster with Cloudera Manager. So this is integrated into management as well. Couple of kinds of use cases we've seen. We've been shipping this to customers for around a year now, I think, if I recall. And we've seen a couple of sort of patterns show up among Hadoop users who are coming to search. One is that you've got some existing data and you can bring more use cases to it. So you may have before been doing some analytics on your data, but now you're able to add search into the mix. So you don't have to move your data. You can take your existing data set. You don't have to create a new silo, a new system. You just enable this new service, and you're not creating another copy across another network. It's all there in the same cluster, and opening search opportunities, so you can get more users of the same data sets. So you may have had certain people who were able to take advantage of your Hadoop cluster before, and with search, you can bring that to a much wider audience. You can get that data that's in there and make it very easily accessible to people in the field, to people who aren't necessarily data scientists or analysts or other kinds of professionals. Anyway, so that's mostly what I wanted to say about the Cloudera Search effort. You can get it. It's, as I said, all open source. It's included in CDH5 in Cloudera's open source distribution. If you use, if you want to try the manager, that's in the free version, Cloudera Express, and you can play with that too. So lastly, before I wind up and take questions, I want to talk a little bit about why I think this kind of matters. So let's step back and look a little bit at the big picture. Cloudera, sometime this last fall, I guess, came out with sort of a new way to think about the Hadoop ecosystem, which we're calling the Enterprise Data Hub. And if you think about it, Hadoop is not necessarily the best name for all this. We call the Linux system, it's somewhat ambiguous between the kernel or everything that runs on the kernel. We use Linux for both of those. Similarly, people have started using Hadoop for the project proper, which is HDFS and MapReduce, but also more generally for the ecosystem. In Hadoop's case, so I'm already falling into this problem. In the Hadoop ecosystem case, it's not clear that there's any one component which is really sacred long term. Hadoop is evolving. It's a bunch of loosely coupled components. We're starting to see things that are looking like they'll replace MapReduce in Hadoop for batch processing. Many of them also support varieties of stream and incremental processing at the same time. We're also starting to see other storage systems beyond HDFS. And so I think there may be a day when we see a Hadoop ecosystem without Hadoop. And I think it's interesting to think about what's the real thing that we have here? What is going on? And what I think is going on is we're seeing a new style of data processing where people build a cluster and they bring lots of different kinds of data to it, and they bring lots of different kinds of processing to it. So rather than the old style of having silos with different kinds of data and different processing running on them and moving data around between silos, instead we have everything combined in one place. And so we're trying to introduce the term Enterprise Data Hub to describe this model of the world, this way of thinking about data processing that we believe is the next wave that's really emerging, and enterprises are adopting more and more all the time. And I think search is a huge part of this. Search really enables a lot of uses of data, a lot of reuses of data that you wouldn't have otherwise, and integrating it in rather than creating a silo for it is a much more cost-effective way and lets you very quickly expose people to that powerful functionality. So that's all I prepped for talking about Lucene. I am happy to answer questions for as long as you want. So I can open the floor to questions now. Thank you very much for having me. Yeah, the question is, what is the difference between SOLR Cloud and Cloudera Search? Cloudera Search is SOLR Cloud plus a number of integrations to make it work well. One is the integration of indexing onto HDFS. So that wasn't something that SOLR Cloud did before. So that's something we brought. Then there's the integration with MapReduce. That wasn't something that was there before. HBase, Flume, and Hue. So it's that package of things, as well as Morphlines. So those were all done as part of a single project, trying to figure out what is needed to take SOLR Cloud, to take distributed search based on Lucene and bring it into the Enterprise Data Hub. The question is, what if you have a variety of different types of data that you want to be indexing?
Yeah, what's the art?
Right. What would you use for that? I think Morphlines would be a good way to go there. I mean, the challenge with a variety of data types is that search is really designed for a bunch of stuff that's in some way similar. So you have to figure out what are the common elements of this variety, and you have to have some logic to do that. And Morphlines would be a good way to express that logic, to how are you going to convert things into some common set of fields. Maybe it's author, title, body, some common schema for all this disparate data, so that it makes sense to put it all in one index that is searchable by one query.
So Morphline is tied to the searching functionality?
It's a separate library. No, and the searching is the interface to searching is a plugin, as it were, in Morphlines. So you could put in other kinds of things, and I think people are beginning to use it for other things. So it's not hardwired in. Morphlines is fundamentally this processor for these config file like scripts. But the sets of plugins are all designed around this flow of events coming in and presumably going out somewhere. And the most common place at this point is Search, SOLR Cloud. So the question is about what was it about a client-side cache in HDFS that made SOLR work more quickly when indexes are stored in HDFS. So it's fundamentally a performance problem. It worked before, but each time you had a query, for each term in that query, it would have to go, and on each of the servers that you're running your distributed search on, it would then have to go into HDFS and open a connection and stream through a file and find the right place in it. And it was very inefficient. When commonly you're seeing the same words again and again, people are searching on the same word. They do one query, they'll do another one. There are certain words that people search on a lot. So there's certain portions of Lucene indexes which generally get kept in memory on the machine that's running the searches. That's the way Lucene has always worked, and it's relied on that for performance. That there's a certain percentage of the index data structures which just get cached. And normally that cache has been the Linux buffer cache, assuming you're running on Linux, the file cache. And HDFS had nothing like that. Every time you seek in a file, it's actually causing remote I/O over the network, and it was a very heavyweight operation and involved making new network connections as well. And so putting a buffer cache locally, that not even a very huge one, resolved this and gave the same performance that we saw with index files that were stored locally. It's not rocket science. It just turned out to be what was needed. And for 5 or 6 years, nobody had seen that. Lots of people had said, "Oh, you can't do that. It's too slow." I think there is a patch in Hadoop to add client-side caching more generally in HDFS that'll eventually work its way through. And so maybe someday it would have been fixed sort of in passing. But this was a nice thing to just get fixed so we could start keeping our indexes in HDFS. And then you get the advantages of if your disaster recovery plans, your security, all those sorts of things by using the same store. Just your disk allocation. If you can have everything in one system, then the way you manage your space can be simplified. So can I talk about how the question is how it handles failure of search nodes and rebalancing the load? SOLR Cloud has that built in. It uses Zookeeper to keep track of which portions of the index are being, which portions of the index effectively are served from which nodes, and when one of them goes down, bringing up a replacement, and managing hot spares if you need, or sharing. So that was sort of already a function of SOLR Cloud that we are inherited in this. There have been efforts to put Lucene indexes in. So the question is that in Google's Percolator, they put the index in Bigtable. And the question was, had we considered putting indexes in HBase? There have been efforts I've seen to put indexes in HBase. I don't think they've been done very scalably or perform very well. I think HDFS is not a bad fit for Lucene indexes. It doesn't tend to create, so the problem with HDFS can sometimes be, for some applications, they naturally create lots of tiny files, and that's a bad use case for HDFS, whereas HBase naturally is designed for containing lots of small items. But Lucene indexes tend to be big enough that they don't cause that kind of problem in HDFS. So I'm not sure there'd be a huge advantage for index storage. I don't remember the details of Percolator. I know that Google uses Bigtable for a lot of other things related to indexing, keeping the, for example, the state of the, or I believe they keep the state of, for example, the web crawl or the data set that they are indexing in Bigtable. I don't know if they keep actually all of the bits of the indexes in Bigtable or not. Maybe I'll take your word that they do. But I don't see an advantage to doing that here. Well, so the claim is that search would be faster if you did that because, so we're not doing indexing with MapReduce all the time. Indexing, that's one mode you can index in with Cloudera Search is doing MapReduce. When you need to do batch indexing, it's the best way to do it. But if what you want to make is have an index that you're making real-time incremental changes to, that's something that SOLR Cloud supports and manages the having parts of the index already stored in disk and parts of it cached in memory. And there's a whole we could talk a long time about how that's managed within SOLR, within Lucene, and within SOLR Cloud across those. But that problem is largely addressed. It will index incrementally at a pretty good rate. Not quite as fast as if you're doing it under MapReduce. So if you really need to reindex the world, then the fastest way to do it is with MapReduce. But if you're just trying to track the world as it changes, it actually does pretty well. So there's cases where you want to, you need to run MapReduce jobs to associate data with the documents you're searching. Think about link conversion. Might be hard to maintain incrementally. Might or might not be. Maybe you could do that all in HBase as well. But that would be modeling the web in HBase. But the natural way that people tend to do link conversion is with a MapReduce job. And then you can associate all of the anchor text, say, of links to a page with that page when you index. And depending on how your data flows through your system, that might end up being a batch process that you need to run nightly. So there's other kinds of processing. I don't want to spend too much time on this, where MapReduce is kind of your only option for indexing. You're inherently in a batch state. Okay, so the first question was, how do I see Elasticsearch versus SOLR Cloud? It's a great question. Elasticsearch is very similar to SOLR Cloud in a lot of ways. It's another scalable distributed search system built on top of Lucene. It was built more from scratch, afresh, rather than in SOLR Cloud's case, they took SOLR, which has been around a long time. And in doing so, I think it's a little leaner and meaner and it's a little cleaner APIs in Elastic Cloud because it's younger. Code tends to get uglier as it gets older, like us. Sorry. So it has that going for it. On the other hand, it doesn't have as many integrations. It doesn't have as many features. So it lags SOLR in some places. So it's sort of a toss-up. The thing that made a difference for us was the governance. That Elasticsearch is tightly managed by a single company. It's not an Apache open source project. It's not a community governed open source project, whereas SOLR is. We felt like if we wanted to, we want to invest in projects that we know we can have some impact on. And it wasn't clear that we wouldn't end up trying to anyway, it looked like it could be an awkward situation. So that was the logic that we ended up with SOLR Cloud. And we're very happy with it. It works well. But it was, the technical reasons seemed like more of a toss-up. So it came down to more governance issues. Second question was, what's going on with Hadoop versus Spark? Well, Cloudera started shipping Spark. Spark is now a part of CDH5. We work with Databricks, and we're big fans of Spark. I think Spark is really a nice next generation engine that does a nice job of merging sort of batch computation, in-memory computation, sort of MapReduce programming, as well as it's can be much more efficient for iterative type programming because it can keep data sets in memory rather than syncing them to disk each iteration, which MapReduce requires. Handle streaming. Anyway, it's a great piece of work, and we think it combines a lot of bits of functionality that people need and that other things are tending to work on in separate projects, but this one project seems to combine a lot of those. So we really like it and are now supporting it actively. Storm's a great project. People love it. I'm one of the folks who helped bring it to the incubator at Apache. So I'm watching that project go forward. Cloudera hasn't yet embraced it in a big way as a part of our product offerings. I think we like the stream processing that's in Spark because it integrates so well with the other kinds of processing in Spark. So you can do stream processing along with your batch processing, along with your in-memory and your machine learning algorithms, and have all these things in one place. And so you get some sharing of what's in memory, sharing of code, of UDF kind of logic. So it seems like a more general platform that attacks some of the same things. So I think the rationale that Cloudera's followed. I didn't make that decision at Cloudera, but that's what I believe is the rationale. But I mean, I think Spark is a great system. Lots of folks are using it. So, I mean, we can't support everything. In general, in the Hadoop ecosystem, you get 3 implementations of any kind of functionality, at least. And ideally, we only have to support one of those. In many cases, that's not the case. We do end up supporting more than one. But we try to pick the one that we want to encourage people to use, that we think is going to be the best long-term solution and be the easiest for them and the easiest for us to support. So at this point, we're betting on Spark.
Cool.
I'm going to go over here for a second. Yeah?
Yeah, what do you see as the future for Avro?
What do I see as the future for Avro? Golden rainbows. I mean, Avro's moving along quietly, becoming the standard data format, one of the most standard data formats in the Hadoop ecosystem. It's supported by just about every component. So I see it primarily as a data format. The RPC mechanism is secondary. Thrift does RPC pretty well. Avro will also do RPC, and there are people who use that. People who love it, big companies that, some of the biggest companies in the world are using Avro RPC and are very happy with it. So it's used, but I think the real sweet spot for Avro, the thing that it addressed before anything else and still does the best job of is data interoperability, writing data in a form that you can pass it to someone else and make sense of it, that you can evolve the data sets, and really thinking about the on-disk format of data for interchange between different applications. Will Hadoop make it easier for SOLR to support auto-scaling? I suppose in some ways, in that it's a platform, it gives it an API already for requesting more instances and so on, but not a lot. I think mostly that's something that most of the work to do that well, to do auto-scaling well, would need to be in SOLR Cloud, and most of it will be the same, I think, regardless of whether you're running on Hadoop or not. I don't know. It would be interesting to see as that moves forward. It's a good question, but I don't really have a strong feeling one way or the other. Sorry. What are some of the most common requests for enhancements for Lucene? Whew, I am not active enough in Lucene to know. I know there's a lot of development going on. There's people are working a lot on things like making. It's a lot about speed. Search ends up being a lot about performance. There's some continued work on functionality and features, but it turns out that a faster search engine is a better search engine. That if people can do 3 searches or 5 searches in 30 seconds, then they find things. They find more things they're looking for than if they can only do 1 or 2. And you really want searches to come back in less than a second. 10 milliseconds on average is great, and that it makes a measurable difference in how much utility people get from the system on whether they can find the things they're looking for, because they can try things quickly and get tired of them. So a lot of work on getting range searches to work more quickly. Getting related thing is location bounded. You want to search for things within 5 miles of something. Very, very common use case. So that's what I see a lot of the work doing. There's been a huge evolution of the sort of the architecture, the underlying plumbing of Lucene to make it considerably more flexible, so that you can plug in different formats of index in there. Twitter, for example, uses a different index format that's optimized for its purposes, and now the Lucene's framework has evolved to the point where Twitter's index format could fit back into Lucene, and other people could use that one if their applications looked like Twitter's, and that was appropriate. So there's been a lot of work around that, just sort of generalizing things. So the way you distribute search, people played around back in the 80s and 90s with various ways of doing it, but the way that everybody ended up distributing search is you do a document-wise partitioning of the collection. So you build a bunch of indexes that have different disjoint sets of documents that they search. So at the top level, if you're adding a document, you need to decide which node it belongs on. So you have some function which assigns some hash function typically, which assigns it to a node, and then it gets indexed. And when you do a search, you broadcast the search to all the nodes. You get their top 10, say, you bring them back to the main node, and you merge them together and present those to the user. So if you're doing this in MapReduce, you just use that same partitioning function that you're going to use in SOLR Cloud for the reduce. So you build one index per shard that you will have in SOLR Cloud. And so you create the data structure that SOLR Cloud expects. And then SOLR Cloud can be started to run on that data structure, on those indexes. The question is, do we see, does it work well when you've got the 3-way replication of HDFS and you run SOLR Cloud on top of that? Does that a good match? There are cases where you think it could perform poorly. We haven't seen those. Where, for example, you might launch a search process which doesn't have any local copies of the index, and maybe not even on the same rack, that it's talking over a switch. If you're doing incremental indexing, that shouldn't happen, because the modified files always end up being written locally first. So you always end up with a copy locally. If you're building your indexes with MapReduce, you can launch things such that you make sure that you launch nodes where they have a local copy of much of the data. So there's not a guarantee, but in practice we haven't seen that be a problem. I think there are extensions to HDFS people have talked about where you try to automatically move data to where it's being repeatedly read. That HDFS automatically rebalances, and that would help here. So far, we haven't seen that as a bottleneck. The symptom you'd see, I guess, is that the switches would start being the bottleneck under heavy search load, and I don't think we've seen that symptom yet. We've got customers who have billion document indexes. I don't know how big their clusters are. I think they're pretty big, and they haven't complained about this. So far, we haven't had to do that. But the question is, are any of the open source search projects trying to incorporate more knowledge or learning? What was the other? Meaning into search. I think to varying degrees, there are people who are doing things like that. I think it hasn't been the sort of semantic search of that sort hasn't been a huge success. I think people haven't done a huge amount of it. These days you're starting to see some pretty robust parsers, natural language parsers. And so I know there are people experimenting with indexing grammatical relations between terms and trying to use that. I haven't seen any open source projects that really that do that and do a great job of it that people are happy with. But other people may. I read research about that kind of stuff. And it seems to be promising. But thank you all very much.